Okay, we are recording. Okay, it's a great pleasure to welcome Dirk Kreimer, who is visiting us virtually from Berlin, and he is going to tell us about algebra and monodromy in amplitudes. Thank you, Dirk.
Thanks, Danjus. Thanks for having me. So this is a talk on, as the title says, algebra and monodromy in amplitudes. So basically it starts with consideration of green functions and then shows that green functions are solutions of certain types of fixed point equations. And you can write these fixed point equations rather elegantly in terms of some Hochschild cohomology. Well, this gives rise to an expansion in multivalued functions. And these multivalued functions are, in simple cases, known as polylogs, and they are also known as generalized polylogs or elliptic polylogs when you go to a higher loop level and when you have more than 3 loops. It's basically not known what they are, but some of their properties are known. The good thing is, which stabilizes the situation, is that the monodromies you get relate to rather combinatoric and algebraic properties of graphs, and there's a rather growing community of mathematicians in graph theory and working with number theories actually, which look into these properties. So let's see what you have. So let's start with recursion quantum field theory. So to go there, we look at the perturbative approach, so simple Feynman diagrams at the end of the day. And Feynman diagrams typically fulfill as a series of diagrams equations of motions. So you have a green function, which is an infinite series over diagrams. You don't worry at the start too much if this is a convergent series or not. Eventually you have to. And these infinite series over diagrams fulfill recursive equations, known as Dyson Schwinger equations. They are 60, 70 years old. You can actually organize these equations in many different ways. One of the most interesting ways is organizing them by what was called a skeleton expansion in older days. The interesting thing here is that the skeletons which give you the integral kernels which drive your equation of motion are also the diagrams which give you the most interesting transcendental input. And if you repeat or recurse all these diagrams into themselves, you're basically just iterating these transcendental numbers into themselves. And so you're getting more and more sophisticated polylogarithms, dilogarithms, trilogarithms, quadrilogarithms, and so on. Now, having all these single inputs, you can actually go the other way, saying I'm not so much interested anymore because I now have this infinite series. I might have even an understanding how I connect it to, say, instanton expansion to make it actually into a truly convergent thing. But each of the terms in my perturbative expansion has an interesting monodromy, which brings me back actually to Landau equations and the analytic structure of Feynman diagrams. Now, this monodromy is of very great recent interest in physics because the people working on amplitudes, they try to organize the computations in computations of, let's say, increasing analytic complexity. And the increasing analytic complexity basically means that you hit more and more mysterious functions which have more and more interesting analytic behavior because they have more and more complicated branch cut structures. So behind that looks a connection to something which is well known to mathematicians in geometric group theory, namely the work of Karen Folkman and outer space, and that's a rather interesting new connection between physics and math, and I want to focus in the second half an hour on that. So let's start with Dyson Schwinger equations. Let's look at the picture, if you like. So let's say, wait a moment, get a pen. This here is, say, indicating the vertex function in quantum electrodynamics. So from the left, we have an incoming photon decaying into a fermion pair. Clearly, there's a contribution from the tree-level vertex function. That's a constant, basically. That's simple. It's a 4x4 matrix, but never mind, it's constant. And then there is an equation which tells you that this function is given by an integral, where in the integrand it appears itself here at 3 different places, and this is obtained by dressing every bare vertex here by this blob, and then you have similar blobs for all the propagators in your theory. And actually, that's the simplest integral kernel. It's just a one-loop integral. That is the next integral kernel, because, for example, this thing is not a good integral kernel because it's just an iteration of this guy into itself. But this is something new. So that's the next integral kernel. And you see there are many places where to plop it. And then the next skeleton is its 3 loops, and it goes on and on and on. You might wish to truncate somewhere if you only have a finite amount of time in your life. Okay, then do the same thing for actually the self-energy, the fermion self-energy. And first of all, the propagator is a geometric series of self-energies. And then we have the fermion propagator showing up here. And we have the photon propagator, and we have the vertex again. And that is an integral equation, which basically determines the fermion self-energy and similarly for the photon self-energy. That's basically already in, for example, the book by Dirk and Drell, chapter 19. Okay, that's old. These are the time-honored Dyson Schwinger equations for quantum electrodynamics, and you can write down, if you are very patient, for the full standard model. It all works nicely. Now behind that is in a way much more structure than people were aware of at the time. So first of all, behind that, there is a Hopf and Lie algebra of graphs, and we basically will focus on the Hopf algebra, the Lie algebra you get by dualizing the Hopf algebra. So first of all, there is a nice little map which you can write down in every dimension, even dimension of spacetime, say 2n. For QED, we would need 4, so n is 2. And it basically says, I give you a graph, and I decompose the graph. The graph tends 1. 1 is basically when you have no graph, so it's the empty set, which serves as a unit in an algebra which is disjoint union of graphs. That's as trivially there. And then you sum over all one-particle reducible subgraphs or disjoint unions of one-particle reducible subgraphs you have. You take them out, and on the other side, you shrink your subgraphs to points, and you get a co-graph. Now, you might actually only take into account those subgraphs which are divergent in power counting. That's then very useful to do randomization for you. And this Hopf algebra basically produces for you a formula like this one, gives you the antipode. And if you evaluate those things by Feynman roots, you get what is known as a counter term of your graph. And when you work this out, you take your coproduct, you take your normalized Feynman roots, you take your counter term, you apply one to the left-hand side of the coproduct, the other map to the right-hand side, and then you multiply together. In C, once you have evaluated, you get a map. That's Zimmermann's forest formula that precisely produces normalization for you. Okay, so that is a nice little structure, but that's just working graph by graph. But then you realize there are nice sub-Hopf algebras living in that. So you make your life a bit more interesting. Say, I'm greedy. I look at all one-particle reducible Feynman graphs contributing to the vertex function. So the lower index here indicates what's your Green's function you are looking at. So that's your external X structure, a photon and 2 fermions. And then you indicate a loop order, say 2, and then you look at the sum of all your 2 loop graphs which contribute to the one-particle reducible graphs you have. That's 7 graphs in QED. And then you work out the reduced coproduct. Basically, the reduced coproduct says, I skip the trivial part, which is always there. That's the interesting bits and pieces. And you work out what the interesting bits and pieces are. And that reveals that actually it's trivial over here. You get a sub-Hopf algebra. Namely, delta of this thing is 3 C1 tens C1, like that, that's that, and that it just so happens there's only one graph at one loop for the vertex, and this here is C1 for the fermion propagator, and this here is C1 for the photon propagator. But it's always true if I would give you a K over here, arbitrarily large, I would have other integers over here, but a sum of graphs would go under the group product for sum of graphs, telling you I have a subhope algebra. That's a very nice story, and the existence of the subhope algebras has been proven for any renormalized field field under the sun. And so you can make a very general setup. You have a Green's function. You specify what is your external edge structure. You specify the number of momenta in the external edges, the internal masses, the coupling constants in your Green's function, and your randomization schemes, and that defines for you the Green's function. And then each Green's function is obtained by actually something which is a Dyson Schwinger equation. Well, not yet. This is certainly giving you just a sum over all graphs with the desired external leg structure, and you're summing basically over all loop numbers. Which you have.
Sorry, Dirk, just your sub-half algebra is a closed system if you fix the loop order.
Yes.
Correct.
That's correct.
Okay. And you mentioned that it needed to be renormalizable. I didn't see why at a given loop order it needs to be renormalizable.
No, it doesn't need to be renormalized, but the subhope algebras you always have completely independent of the question of renormalization. Okay, good. Mm-hmm. But when you have the subhope algebras and you use it to renormalize, then because you have coefficients which are indexed just by the loop order, then the counter term for this guy gives you precisely the counter term for the K loop graph. That's very cute because then this gives you multiplicative renormalizability. Okay, now you define your series of an all infinite series over graphs created by the loop number and so on.
Can I ask a question?
Excuse me?
Can I ask a question? Okay.
Yes, please.
What kind of half algebra is it? Is it co-commutative, quasi-triangular?
It's a graded commutative, but not co-commutative half algebra. The dual of it is the universal enveloping algebra of some non-abelian Lie algebra. So, and this Lie algebra has a flow around unities, so to speak, which gives you the normalization group flow.
Is it quasi-triangular?
Excuse me?
Is it quasi-triangular? Is it an R matrix, universal R matrix? What?
It's hard to understand you. I'm sorry. Please repeat.
Okay. Is it quasi-triangular? Can you hear me? Quasi-triangular.
Yes.
It is.
It's basically very similar. Now I don't know of a. No, it's very closely related to the Hopf algebra which runs the diffeomorphism groups. That's probably the near closest cousin you might have been familiar with.
Okay.
And okay, so now we have a little bit of notation for renormalized things. And then the beautiful thing is the sum of an infinite number of graphs can be written basically by a sum over just graphs which are primitive under the Hopf algebra. So they fulfill this. And these graphs are precisely the skeleton graphs I mentioned before because they don't have subgraphs which iterate into them. They are just the driving integral kernels. That makes it a much more structured equation of motion which you have here, because now you have actually these nice little integral kernels, and this map B plus is basically saying I take a little subgraph gamma, like this one, and it takes the argument, and I plug the argument into the graph in all possible places. This is an innocuously looking map, but it's actually not such an innocuously looking map because it is actually a Hochschild 1 cocycle in the Hochschild cohomology of this algebra. This actually makes for very nice integral equations, gives the Schwinger equations very manageable structure. One thing which comes up when you look at it is that if you have a vertex function, then the vertex function is always, you can define the Green's function for the vertex and divide by the square root of all the Green's functions for the external edges on the vertex. And you take the square root because you're really looking at external half edges only. Two fermionic edges here as well. And so the square root squared is just that function. And that gives you what in the old literature was called the invariant charge, going with a coupling in your theory. And basically, this is the structure here, which is universal for all renormalized Green's functions. You have your function you are after. On the left-hand side, it appears linearly on the right-hand side, multiplying invariant charges over here. And if the invariant charge is a constant, which basically tells you that the logarithmic derivative of this thing when you evaluate by the Feynman rules is 0, which tells you that the beta function is 0. So when the invariant charge is 0, this is a linear fixed point equation, which has a scaling solution, which precisely tells you when the beta function vanishes, you have conformal symmetry in your theory, which is just about right. And this is maybe already almost as much as I wanted to say about the Dyson-Schwinger equations, how they are structured, are set up, and there's a large literature, for example, Gerald Dunnan's, which people use the structure to come to non-perturbative solutions for Green's functions, relating this to resurgence theory of Ekal and all these type of things, connecting it to instanton expansions and renormalons and whatever. It all starts from here, but that's not the main topic. What I really want to look in now is the little gammas up here. The little gamma.
Sorry, can I interrupt? Can you hear me?
Yeah.
Okay. The subalgebras you are getting, are there ideals or?
No.
No, they are not.
No. The ideal, there are interesting co-ideals actually in this algebra. And these co-ideals come as you may give you a gauge theory. And you try to answer the question, are these sub-algebras there for gauge theory? Now we know in a gauge theory, you have Slavnov-Taylor identities, which basically tell you, for example, that the invariant charges for the free gluon coupling and the invariant charges of the coupling of a gluon to a fermion pair and of the coupling of a gluon to a ghost thing are basically all giving you the same coupling constant, and giving the square of that coupling constant is then the coupling constant for the 4-gluon vertex. Yeah. Now, with loop corrections, this gives you the Slavnov-Taylor identities. Now, if you want to see how the sub-Hopf-algebras are there, they are there because Slavnov-Taylor identities correspond to co-ideals in this Hopf-algebra, and you have to divide through by these co-ideals, and in the quotient you find your sub-Hopf-algebras, and these sub-Hopf-algebras are just quotients. And then, when you divide through by the Slavnov-Taylor identities, the story is the same. But you really have to fulfill that your Feynman rules fulfill actually the Slavnov-Taylor ideals, which means they precisely vanish on these co-ideals. Okay, so now I want to go through our little graph gamma. So basically I want to look at, say, a given Feynman graph, maybe some graph which doesn't have divergent subgraphs, and want to understand a little bit what is actually its monodromy and what is so exciting about a single Feynman graph. And eventually, one fine day, and we are not that far off, I believe, all these local excitements graph by graph will add up to an excitement for the full Green's function. So, what do you need to do when you want to evaluate a Feynman graph? Basically, you need to define two graph polynomials, psi and phi. So what we do is we have some Feynman graph. For each internal edge, we assign a positive real variable, AE. That's basically the length of that edge. And we want to integrate over all that length. And this gives you what is known as a parametric representation, and it's built on two polynomials in these variables. Traditionally, they call it psi is a semantic polynomial, and phi is a second semantic polynomial. You define them using spanning trees and spanning forests of your graph. So the simpler one is psi polynomial. So you take a sum over all spanning trees in your graph. So all simply connected subsets of edges and vertices, which cover all vertices of the graph. And then you take a product over all the edges not in the spanning tree. And then you take the product of these variables. So this has three edges here. And any two edges of this graph form a spanning tree. So this has three spanning trees, so you can take A1, A2 plus A2, A3 plus A3, A1 would be the psi polynomial. That's a simple polynomial. Then actually you define Q of V for every vertex V in your graph. You look if there's an external half edge running into it. If yes, the external half edge is assigned an external momentum in Minkowski space. There you call it Q, and so we have for each V a Q. It can be zero if there's no external momentum at a given vertex. So we let Q of V with external momentum entering at the vertex V. And for any subset of vertices X, you let Q of X to be the sum over all vertices in X, the sum of these Q of V. Then actually you look at two forests of your graph. So two forests of the graph are disjoint unions of two trees in your graph, which are disjoint, which together cover all vertices. Both of them are supposed to be trees, and we count a single vertex as a tree. So this graph has three two forests, namely this vertex and this edge, or this vertex and this edge, or this vertex and this edge. Then you take a sum over all these edges not in your two forests, and again you take such a variable and you multiply this with the scalar product of all the external momenta ending at the vertices belonging to the one tree, scalar product with all the external momenta entering at the other. And because the sum of all momenta adds up to zero, that's momentum conservation. Q of T1 is minus Q of T2, and you get an elementary identity. Now, okay, you have the two famous semantic polynomials. Now you actually make the phi 1 to a capital phi 1 by taking it, take the small phi 1, which we just defined, and multiply it by m of gamma. M of gamma is just the sum of all edges in your graph, and each edge might have an internal mass. Again, it can be zero, but must not be zero. And so you multiply each edge E by the mass squared. If there is a mass in that edge, that gives you that quantity, and you simply modify this a little bit by taking the first semantic times this. Note, this is a homogeneous polynomial. This is a homogeneous polynomial. This is of 1 degree higher than this polynomial, but this polynomial is linear in AE, so this is a homogeneous polynomial again. These homogeneous polynomials fulfill nice properties which are very well studied in mathematics. For example, for any chosen subgraph, little gamma of your graph, this factorizes where this is always of higher degree in the variables of the subgraph than psi of little gamma, and this is of higher degree than psi of little gamma, and this is of higher degree than psi of little gamma. And there's a little typo here. This should be a boldface. Phi. Also for disjoint unions of graphs, we define it like that. And there are a couple of other nice identities you have. These remainder identities, you can look up graph series paper and collect many useful combinatorial properties down there. Francis Brown and I showed a couple of years ago, I think it's frightening, more than 10 years ago, that, or almost, that precisely the property of these remainder polynomials make, together with this Hopf algebra, for an elegant proof of renormalizability for any renormalizable quantum field theory. So what are your Feynman rules actually in using these polynomials? So I define first of all an integrand for you. I don't want to integrate it yet against something. I give you just a form. Int of a graph G, I call it. It depends actually on Q and P. P is actually a point in the projective space P, number of edges in G minus 1 over the reals. And so this is spanned by your edge length. This is given by your AE variables. And the Q is a joint notation for all the external momenta which you have. And I even don't mention the dependence on the masses because the masses are fixed parameters for me. Then the form, your integrand you're looking at, is a sum over all forests in your graph. Forests in the sense of Zimmermann, these are just the number of components of the antipode in our Hopf algebra, minus 1 to the number of components in here. And then you get the numerator and the denominator. The denominator is just a product of the psi polynomial squared. For the graph G, where all elements of the forest shrink to points, so that's basically a co-graph or co-forest, if you like, and actually psi squared of f, and because f has disjoint components, we actually use that psi on the product as a product of the psi evaluations. And for the phi polynomials, there is a similar rule, which starts here means I have determined my normalization scheme. Because it's only the big phi polynomial which depends on external kinematics, and the kinematics values of external momenta are what they are, but I want to actually subtract to renormalize at a fixed value of external momenta. And that choice of fixed values I indicate by a 0 over here. So that shows up here, and this whole log would be 1 if I would put a little 0 in here. It's just not 1 due to the deviation of this thing from being evaluated at the normalization point. There is where all the monodromy is coming from, because all the monodromy in Feynman graphs is inherited from the monodromy of the log. This here is a standard form in projective space, just the alternating sum of the edge variables. And that's therefore a number of edges in G minus 1 form this thing altogether, because the coefficient is just a function. Okay, now we have a wonderful form. What is then the renormalized Feynman integral? Well, it's simply taking this form and integrating it over our projective space, which is simply called PG. And that's a proven fact that this integral exists and gives you a finite answer. So that is by construction, if you like, a log rational function of P, which is well-defined, totally well-defined in the interior of the simplex AE, all AEs greater than 0, because it's a point in projective space. You cannot have that all AEs vanish simultaneously, but some could vanish and actually approach a boundary of that simplex. But in the interior of that simplex, this is a completely well-defined form, and you basically inherit your monodromy because actually some zeros, some interesting points of your form here touch precisely the boundary of the simplex. There are no poles at the boundaries, but there is interesting behavior. Now, let's try to understand. Yeah.
Your arguments here seem to be dimension independent.
No, because
You,
that brings the dimension D. I agree, I just said D equals to 4 once we went up to this slide. If you want to have your dimension back, this 2 and this 2 are really D half.
okay, and did you in your renormalization prescription? It wasn't clear to me what prescription you had chosen, or does it matter?
It does matter. You get finite renormalized, different finite renormalized quantities for different renormalization schemes. So here I'm basically using things like the BPHZ or any kinematic subtraction which subtracts on the level of the integrand by fixing external momenta. It's so basically kinematic renormalization scheme. If you would say I would like to have minimal subtraction, we can do that. In that case, I would keep that D over here. I would actually have a couple of AEs to the power D half minus 2 hanging around, which is just giving you an epsilon. I would take the limit epsilon goes to 0 and evaluate my antipode and make the rule I'm only throwing away the pole parts. And then I get again a finite quantity, and it would be the MS bar result. But I'm basically looking at these type of renormalization schemes because algebraic geometers convinced me that in minimal subtraction, the transcendental number content of the theory is arbitrary, but it's very nice in kinematic renormalization schemes which have a well-defined S matrix.
Did you define co-unit?
My co-unit.
And what is its meaning? What is the meaning of co-unit?
The co-unit, I basically only need how to define my antipode. And the co-unit is basically a very simple one. The unit is my empty set, and the co-unit on the unit evaluates to 1, and it projects anything in the augmentation ideal to 0. So it's an extremely simple co-unit. So this is a graded algebra. J running from 0 to infinity, Hj, and J running from 1 to infinity is the augmentation ideal, and H0 is basically isomorphic to Q times 1. So it's a connected, positively graded.
Okay.
Okay.
Sense to talk about the star of this algebra?
Excuse me?
Is there a star defined on this algebra? Is there any meaning? Is it what star?
There is by Milner-Moore a well-defined dual, which is a universal enveloping algebra of Lie algebra. But if you like to discuss the star deformation or anything like that, no, there's nothing like that. At least Victor Kutch and people around him looked into that, and they say, no, these type of algebras have no good deformations in that sense. Okay, so now we come to something which looks completely different, and that's for me a very exciting story that this connection does exist, namely there's a connection to something which is called the cubic chain complex, and we have to see what this is. So instead of looking just at a graph G, I want to look at a pair of the graphs G and a spanning tree T for it. Okay, and you can define, if you like, a Hopf algebra for such pairs by just looking where in the ordinary Hopf algebra the pieces of the spanning tree go. And a couple of consistency conditions, but that's easy to work out. And clearly, the Feynman integral is independent of the choice of a spanning tree, as long as T is a spanning tree of G, because you can follow the rules. All external momenta always flows through the spanning tree. This is possible by the definition of a spanning tree because it connects all vertices. And then basically choosing a different spanning tree just means choosing a different routing of your external momenta through the graph. And by translation invariance of your initial measure in momentum quadrics of your Feynman integral, it's independent of the choice how you route your momenta. but things which are properties of a pair of a graph and a tree, and which are invariant properties of such pairs, invariant of the choices of trees, span something which is called Kahn-Vogtmann's outer space. And we see an example in a second. It assigns a cell C of G to any graph G, and the Feynman integral, as we have it with our Feynman rules, becomes an integral over the volume of the cell. We see an example in a second. This is obvious in parametric space, where we can identify the edge length of an edge with a parametric variable. I give you a very simple picture. Here's the simplest graph under the sun, namely the one loop bubble. I take two different masses, M1 and M2, indicated by green and red, and I take one of the two edges to be the spanning tree, indicated by a double line. On the left side, I assume that one always assumes that the spanning tree is of the edge, an edge in the spanning tree is of smaller length than an edge not in the spanning tree. So here the red edge is of smaller length than the green edge, so the red edge is the spanning tree. Here, in the midpoint of my cell, actually green and red are of equal length, so I cannot decide where my spanning tree is, and here on that side, it's vice versa. Now, if red completely shrinks, I get a little tadpole graph, and the two external half edges would hang around like that, and similar over here. It turns out this is a very crucial point in outer space, and it turns out I can identify it one-to-one with a point where such a graph has monodromy, namely such a graph has monodromy when q squared equals m1 plus m2 squared. This fixes I only have one external kinematic variable in the graph because I only have one external momentum, and it's now fixed to by my given masses, and that has monodromy when A1 M1 equals A2 M2, or in my projective one space, which belongs to this graph because it has two edges, so it's a projective one space. It is where A1 over A2 equals M2 over M1, which is really the point where I define my midpoint to be. So it's a midpoint in a slightly deformed geometry, which is given by this. So here is my monodromy. And this actually, later on, we will see that to such a graph, I can make nice little Hochschild matrices. Here for the integral, where the A green variable is smaller than the A red variable, that gives me a part of the integrand. And this has monodromy at this point. And actually it has a reduced graph which lives above here. And that's actually a little Hochschild matrix. The variation of this graph when I vary q squared is given by this thing. And this thing is basically a constant as far as logarithmic variation goes and has no further monodromy. And this is actually a tadpole graph, which is a constant and has no monodromy at all. So that is basically a very simple role model. Now, outer space is really by gluing the cells together, which basically tells you have different graphs which they have the same number of vertices, so they belong to the same entry in my subhope algebra. And they have, for example, if I shrink a certain edge, for example, I can shrink this edge, and I go here, and I can actually shrink this edge and go here, or shrink this edge, go here. So these are three different cells which have a common codimension 1 boundary. That's the way these cells are glued together. In outer space, and or vice versa, you can take one graph and look at all its boundary codimension 1 cells. You can have 6 possibilities to shrink an edge over here, and you get to a quite colorful array of graphs. And if you keep shrinking and shrinking and shrinking internal edges for any chosen spanning tree, if you shrink all internal edges in a spanning tree, this is a three-loop graph. You always end up what is known as a rows in outer space. And outer space basically considers, because the phi1 of such a thing is just a free group of three generators, the outer space uses graph theory to study representation theory of the free group on a number of parameters. And it uses graphs, bridge-free graphs in particular, which have as many loops as your free group has generators. But all what you do in outer space has a role in physics. So let's go there. So we want to study cells C of J, and with for each cell C of G, which has associated reduced graphs when edges shrink, we in particular look at the barycenter corresponding, then the barycenter of a cell is the point where all internal edges are on shell, or to put it like that, where all edges have the same length, measured relative to their masses. Such barycenters form something which is famous in outer space, namely the spine of outer space. Please be a little bit patient, we see a picture on the next page. So the barycenters then provide coordinates in parametric space for the threshold divisors, namely for the points where your monodromy sits for all your Kreimer amplitudes. Physical thresholds are determined by solving a variational problem, namely you actually have to minimize your edge variables to find where your extremum are in these cells, and well, that gives you the leading singularity of the thing. And now comes something which is really very interesting. These spines, as we see in the next picture, define cubes for you and visit many, many paths to go from the midpoint of the cell to the roses at the end. And each such path defines a lower triangular matrix for you, which is a Hodge matrix. And if you collect all these Hodge matrices, you start understanding your monodromy, which you are after. So this turns it all into some sort of algebraic geometry at the end. So actually, I think it's time to look at an example. So here I take my wonderful little graph and I take just the one loop triangle graph on three different masses, blue, green, and red. Here these little dashes indicate that all three internal edges are on shell. So this is what is known as the leading singularity of the graph. Each propagator gives you a function which is a theta function of positive energy in that edge times a delta function, or which is the on-shell condition for that edge. And this sits precisely in what I define to be the barycenter of this big triangular cell. It's an accident that the triangle graph has a triangle as its cell, but that's the way it is, and it's the last thing which you can draw on a two-dimensional paper, so to speak. Okay, so here sits that. Now you move. That's the path in the spine. You move to codimension 1 boundaries by shrinking something in your graph. So for example, you keep blue and green to have the same length, but you shrink red. You're precisely ending up in the barycenter of this codimension 1 boundary here, and you end up in the codimension 1 boundary here and here, either on these two masses, or these two masses. And when you keep shrinking, meaning you are leaving the point where the edges have equal lengths, you go to this side or this side, and you end up in a rose, which is a one-petal rose because you only had one loop. So this defines three cubes for you. Cubes given by those four edges. And there's a similar cube here, and a similar cube here. And people in geometric group theory, or actually people in graph complexes Yuri, like Maxim Kontsevich and Karen Vogtmann and Thomas Wilwacher, they studied these cubes for many years in great detail. They have all sorts of nice things to say to mathematicians, and this is also now good for physics. Now let's look at these cubes actually. So let us study one cube, say for the spanning tree, and on blue and red edges, so which means it goes to the rows which is on the green edge over here. So the cube gives you 1, 2, 3, 4, 5, 6, 7, 8 edges on its boundary, and it has the inhabitant over here, which is this graph, which moves around and with different edge lengths. So it's sitting somewhere in this cube. For example, if blue is longer than red, it might go to this boundary, and if red is longer than blue, indicated by the black dot, it goes to this boundary, and it's somewhere in the middle. Okay, so this gives you 9 graphs. Here is the thing where blue and red can shrink, and green I keep simply on the Mars shell because I can put any rows on the Mars shell without a price. And then I have my rows here, and I have my graph here, and I have the leading singularity here. And that gives me one triangular matrix and another triangular matrix. So I get 2 triangular matrices from one cube, so I get 6 triangular matrices from this graph. And maybe I have them somewhere. And here's one of them. So this is basically all there. This column and this column are only there to make connection to standard conventions of physicists, which are very interested in these matrices, and they discover them by just studying them integrand, at least in simple cases. Actually, they only can study one cases at the moment, but the construction graph theoretically holds forever. So here are my entries. I get my full graph here with the blue edge longer than the red. And here they have equal length. So I put them on the Mars shell. So this is already a Katkowski cut. And this is the leading singularity, which is also a Katkowski cut. But that's a normal threshold, precisely where the incoming momentum squared here equals the sum of the 2 masses in here. And it's the same threshold as this reduced graph would have. And here is a much more complicated threshold starting off, which is the annular threshold of the triangle graph. And actually here I have the reduced graph where the red edge shrinks, and then when the blue edge shrinks, I get my constant tadpole graph. And this is a Hodge matrix. The variation of this column is given by this column, and this column still has a variation because I have an integral here over the length of the red edge. This is a logarithmic integral. It has a variation because the log has a variation, and that's given by z over here. And this just tells you the ordering, the sector decomposition of the length of the edges for this example. Well, you get, as I promised you, you get 6 of those guys. And then you actually might wish to add them up in one big matrix, which you can do. Yep, and it looks somewhat like that. And that matrix is interesting for physicists because when you look at recent literature on amplitudes and contributions to amplitudes coming from single graphs, basically it's all discussing so-called coactions. And this goes back to work in algebraic geometry, mainly done by Francis Brown, which tells you you should study actually a map which takes a Feynman graph and consider it as a realization of a motive somewhere. And then you should have a fine, nice map which maps the Feynman graph, which sits in a set of motives, to motives tensor de Rham classes. And the de Rham classes are precisely the integrands which you get for graphs which have edges on the March shell, and the motives are graphs where the edges don't separate the graph into two pieces. So you are only putting your roses on the edges in your roses on the March shell. And then you work out a coaction which tells you the coaction, say, of such an object. Actually, for physicists, you like to start here. Is this object times this object, something like that, and then this object times this object, which you have here, and so on and so on and so on and so forth. And that gives you a nice little map which acts like a coaction on such Hodge matrices. And then Francis Brown explains to you, if you have these Hodge matrices, it tells you something about where monodromy can contribute and where not. These matrices have a couple of properties. Every entry on the diagonal are group-like, and the tadpole graphs are extremely simple, especially in a kinematic optimization scheme. This guy is 0, and this guy is 0. So is this guy, obviously. So that simplifies life a little bit. And if you simplify your life like that, you can, in a kinematic optimization scheme, things get a little bit simpler, but they are still complicated enough that for a one loop triangle matrix, you get something, a triangle graph, you get something like a 1, 2, 3, 4, 5 by 5 matrix. That's not too bad. But if I give you a graph which is in high demand these days, that is a wheel with 3 spokes, that's a 3 loop graph, which has 16 different spanning trees, and you have 3 possibilities of ordering the length of the spanning trees, and you have 3 possibilities of ordering the length of your petals. That makes 16 times 6 times 6 different Hodge matrices. So that's 572 Hodge matrices to understand the monodromy of that graph. So it explodes rather quickly, but it's rather systematic. Okay? So now what is the general structure of these things? What you have? Well, you have the graph, or certain vector of the graph ordered by edge lengths you are interested in. Then the variation of this thing. So you look at the special divisor, and there's a log in the integrand and the log at a certain pre-described variation, so you get the variation of this graph. This is precisely the Katkowski rule, basically, which brings you here, and that has a variation, which brings you here. In the best of all worlds, you can invert this map and go back, have a dispersion relation, and you can actually, you see, this part is here and the same part is here as well, just those 2 edges on the March shell. So the only difference is that the red edge is on the March shell here and not on the March shell here. So you have a dispersion relation which actually brings you back from the 4-point function where the internal propagator is on the March shell to this, which goes from here to here. And if you know that dispersion relation and can construct this thing, and you know where the anomalous special divisor was for this graph, you can actually write down a dispersion integral to go back from here to here and reconstruct this graph from knowing those entries and actually also knowing the diagonal. Well, that was supposed to be here and knowing the diagonal entries. So you know your diagonal, you know your subdiagonal, and then you know your entry here. And this basically comes from the fact that you have a boundary operation on your graph where one of the 2 boundaries actually shrinks an edge and the other boundary puts an edge on the March shell. And these boundaries actually give you really nice boundaries. They are real boundaries, they square to 0. And this is what Karen Frogman has studied when she was studying outer space in geometric group theory. And she learned from that a lot about the representation theory of the fundamental group of graphs. And we learn about the monodromy. Okay. So a variation basically induces a transition from one column to the next, which you want to invert by a dispersion relation. This gives you a Hodgman matrix. And if you look, this has 2 edges, this has 3 edges. So this is an integral in projective 1 space. This is an integral in projective 2 space. There is 1 dimension different. That's precisely this integral is a vibration over a base space provided by the integrand from here. So there's a nice vibration story going on. I think I still have a couple of minutes, so I want to go maybe to some example a little bit. The triangle graph in concrete quadrics where M1 is really small mass 1 squared plus iota, to give it as imaginary. But that are my 3 quadrics. You can integrate them directly in momentum space land if you like, and you will find a nice little threshold divisor. This is the famous omnus factor here. You can write this as a Chilean function of the 3 external momenta. It basically tells you what the anomalous threshold is. Where the anomalous threshold is slightly more complicated, but you can work that out as well. And that basically comes from evaluating your Feynman rules when all 3 internal edges are on the Mars shell. An anomalous threshold appears when you are below the normal threshold and above the pseudo threshold. And you can also leave that propagator uncut. It gives a different entry in our Hodge matrix, namely this one. And this has a nice factorization structure. It comes basically as a result, which is a variation of this graph. That variation is given by putting them on the marshal, so that's over here. And then this is just the factor you get by integrating this Feynman graph of all possible values of the momenta in this momentum transfer from here to here, which is really an angle integral because the external momenta are fixed, but the angle is kept free. So, yep. There's clearly fiber dimensions are different. That explains a certain factor of a half. Coming in, a couple of nice things you can do, and you get your normal threshold is precisely again the normal threshold of this graph. Fine. The anomalous threshold comes in a lengthy calculation, which people can do. And it's again an expression completely given in Chilean functions built from external momenta and masses of the graph. It's correct in the literature in one place. For example, it's not correct in Itzig-Zuber. It's correct in Itzig-Zuber in the equal mass case, but they have serious typos when the masses are different, so that has confused many people. But in some old papers, I think not by Farm himself, but by one of the collaborators, is the correct computation of this thing. Okay, you can actually, if you are now a graph working in graph complexes, you can actually look at these boundary operations of Kahn's-Vogtmann and look at graphs, permute edges, and realize you can actually find nice looking generators of, say, 1 cocycles. In the one loop case, you're just looking at 1 loop graphs, and 1 loop graphs have been very well understood, not more than that. And that's basically my example. Now, if you do 2 loop graphs, the same thing happens, only everything becomes more complicated, obviously. In particular, you have many more edges, and you have many more sectors to consider. And actually, it's a rather interesting combinatoric game. You have 24 sectors because you have 4 edges, so that's 4 factorial sectors which order the edges by edge lengths. You have 5 spanning trees in the graph, and 2 sectors coming, which 2 edges in the spanning tree are larger and smaller. So you have to actually ask yourself how the 24 sectors decompose over these ordered spanning trees, and you can work that out. It's in a recent paper, and actually then come a couple of results which are important for physicists maybe. First of all, your initial Feynman rules can be written as Feynman rules which precisely operate on pairs of a graph and a spanning tree, which means you can formulate your Feynman rules for every paper which Karen Vogtman ever has written, if you like. Then there's a coaction, which we'll simply call delta of G, which is the sum of the coactions which you build for each little matrices, which we looked at above in any loop order for any graph, and you have to glue them all together. And this gives a nice coaction. And that it is a coaction means it has to define a couple of identities, which it indeed does. And that's actually the coaction which agrees in all computed cases where Feynman graphs could really be computed. And the way physicists find these coactions is they compute a Feynman graph. Now, this is generically only understood for one-loop graphs, but we know that all one-loop graphs give dilogarithms. Now, the coaction of a dilogarithm is known to map to a log, tens log, where one of the logs is actually really an Li1 and the other is, so to speak, an ordinary log. But it goes basically to log tens Li1. That's well understood and proven in algebraic geometry, so you can work out by reverse engineering what is the coaction on graphs when you look at one-loop Feynman graphs by computing them, get a result in terms of dialog, apply the coaction of the dialog, and get something where you then see that the left and the right hand side can precisely be identified with reduced graphs or graphs where edges on the mass shell. So physicists could back reverse engineer this, and we agree with this on one loop, but on more than one loop, they don't have yet a full answer, and this gives from the mass side a full answer what a coaction is. We could probably prove using the Feynman rules that it really gives the right physical answer. There are a couple of two-loop things where it does work, but we would like to do a complicated two-loop graph to show physicists really how to do it. The problem is that the simplest Feynman two-loop graph where you can do it is this one with 3 different masses. There it works, but it gives you an elliptic dialog, which is a function which is yet not fully understood on the algebraic geometry side. So we wait a little bit until this is better understood on the algebraic geometry side, because algebraic geometry has not yet a definite answer what the coaction is for this special function. Actually, it has two different answers, and it's even not yet clear if they agree or are slightly different. So that is something where algebraic geometry is working, and I think I don't want to say much more apart from, if you really take the Dunge's cap, it has 4 edges, so it lives in a 3-cell, which is a tetrahedron. Now it has spanning trees of length 2. Spanning trees of length 2 give you ordinary 2 cubes. So you can't dissect a 3-dimensional space into 2-dimensional cubes. So beyond one loop, the dissection between cubes and the cells of outer space is not that nice. Actually, the mismatch in dimension is precisely coming from these fiber integrals I were mentioning. So actually, what you get here is a decomposition of the tetrahedron of some bases inside into 5 different cubes, because you have 5 spanning trees. And over each cube, you have a vibration which then completely fills the tetrahedron. And it's ongoing work of people in graph theory land to prove how these vibrations look for any arbitrary Feynman graph under the sun. And then I played this game with orderings of spanning trees quite a while. And let me come back and finish my talk. It's coming back to Dyson Schwinger equations, but now for outer space, if you like, namely for graphs which do have Katkowski cuts, meaning I take graphs, have a Hopf-algebra on pairs of a graph and a spanning tree or spanning forest on it. So here I look at a graph which has 1 incoming line, 2 outgoing lines, and the incoming particles and the outgoing particles are separated by a Katkowski cut. So the graph is always cut by a cut which puts internal edges on the mass shell. So then actually, this gives you a Dyson-Schwinger equation, which has now many more Green's functions coming in when you go to skeletons of higher loops, because there are so many ways how to cut a graph, but it's still a Dyson-Schwinger equation and it's still a fixed point equation, and you can still actually look at the structure and learn something about the analytic structure of Green's function at all loops. And then there's an interesting aspect, that the co-action structure which you have over here. Let's say delta co, and the Hopf algebra structure which we started the talk with for randomization. They both operate, if you like, on graphs, and they actually agree, or are, say, co-interacting with each other. They are consistent with each other. They gave what is these days, that is a very new notion in Hopf algebra, a co-interacting bialgebra. Actually, there's work by Leuk and some collaborators who discovered this notion in the last 12 months. And there are some preliminary papers out, and there are very good slides of Leuk of a talk he gave on this out. And I have a preliminary version of his final paper on that, and the final paper will probably be on the web in a couple of weeks. So there is a notion of a co-interacting bialgebra. The final message is that our little co-action of Feynman graphs, our little co-product for randomization, are precisely forming a co-interacting bialgebra, which basically tells you that you can renormalize graphs with Katkot cuts precisely as you think you can. And there are a couple of conclusions which basically tells there's much more work to be done. That's it. Thank you.
Thank you very much, Dirk. We are a rather silent format for applause, but we do our best.
Thank you.
And the floor is open to questions.
Question. Yeah, well, I have several questions, but let me start with one. In the beginning, you said, well, when you work with Feynman graphs, you really don't care if the series converges or not.
Yes.
In the examples you have, do you see particular features which only happen when the series converges, or is that too early?
No, basically, let's put it that way. By construction, every renormalizable quantum field theory gives you an infinite series of graphs, and basically they never naively converge. But let me explain a little bit the work of those people and collaborators, because it directly relates to the talk and your question. You can turn your Dyson-Schwinger equations written in terms of these B plus Hochschild code cycles. At the end of the day, you can turn them into nonlinear ordinary differential equations. Now, nonlinear ordinary differential equations have a formal perturbative solution. Namely, you say, I try to solve them by some ansatz, which is a formal power series, and you might get a recursive relation as a solution between the coefficients. This is not yet giving you a convergent series, so it's not yet giving you a solution. But what you can do is, you can take the theory of this resurgent series, and the theory of resurgent series, say you have one formal series, fx is some Cn x to the n, and you know a recursive relation which determines the Cn. That's not yet a convergent series, but then there's a theory which tells you all such series at the end can be expanded not into such a series, but into such a series plus a different series, which is again has different coefficients, dn if you like, and a e to the minus 1 over, say, a small parameter x plus an f2 e to the minus 2 over x, and so on, plus something which might be another series, say g1, which is a series, formal series, times a log of minus x and a G2 involving a log squared of minus x and so on and so forth. And there's a big theory of Ekal, which says every nonlinear ODE under the sun can be solved, probably solved by fixing boundary conditions and taking such expansion. Okay, that's fine. That's a piece of mathematics which is known since maybe 20 years. The rather recent thing and conjecture of Ekal, which is now about to be proven and used in applications in study of nonlinear ODEs, is that these F1 and F2 and G1 and G2 are not independent of these formal series, but there is a well-described prescription depending on the chosen boundary conditions and on the Stokes factors of your ODE, which tells you how to get F1 by derivatives on the F on F over here. So this gives you just some rational multiples of the Cn and so on and so forth. Or actually, the F2 might be involve some F squared or F prime times F or something like that. But there is a complete machinery which tells you how you get your F's and your G's. So in principle, you can use that to really get to non-perturbative solutions over here. It's very hard business. It has recently, about a year ago, been done by Michi Borinsky and Gerald Dunn for that simple problem. You try to solve, to iterate into each other, all one-loop Yukawa bubbles. So you take this graph, plug it into itself in all possible ways. This gives you an uncountable number of diagrams. And this is a solution when you write down the Dyson Schwinger equation, which is just based on one driving integral kernel coming from the one-loop graph. This gives you a nonlinear ODE, which is quadratic. So you have something like gamma is something involving gamma squared and something involving gamma times gamma prime and something basically a constant over here and some coefficients, and I can't remember the sign. So you get a nonlinear ODE. You can show that this nonlinear ODE as a series gives you a series which is basically the complementary error function, and then you specify your boundary conditions, and then you get all the nice little flat contributions, if you like. In principle, Borinsky and Dunn and collaborators say you can do this for any Dyson Schwinger equation under the sun. The thing is, you would get a system of nonlinear ODEs, and these are by no means very simple systems. But in principle, research theory should handle them, and I think the next project of these people is to start with gauge theory. Gauge theory are nice because gauge theories give you enough Slavnov-Taylor identities that you might get away with a one single equation for the better function, say, of a gauge theory. And that is what they try to do now. But in principle, you have to be very smart to understand the structure of your perturbative thing. And so the perturbative solution is not convergent, but in it, it carries the information about all the non-perturbative terms you need to get to a real solution. That's the message which these people have.
So concretely, for gauge theories, you would want to expand also about instantons or the instanton moduli space.
That is true, but the message these people have is that because the Ekal ansatz would precisely say you should make this ansatz, which is basically an instanton ansatz. If you say this is your little coupling constant G, then they would say, okay, I make an ansatz which says I have given my perturbative series. I don't know anything about instantons. I believe that the true solution has instantons, and maybe this is not needed for gauge theories. Maybe it is, we don't know yet, but it has instantons and renormalons or something. And then Ekal would tell you, but then if you know your ordinary differential equation, I can predict how to get these coefficients in front of the instantons from this by manipulations which involves just multiplying the series with itself or with its own derivatives. And that is theorem of Écart, and this theorem is put to the test if it really works in physics and quantum field theory by these people at the moment. I'm very much looking forward and hope that in 1 or 2 years we have an answer down there. It's not
Very good.
Can I ask a question?
Go ahead, Arthur.
Yeah. So, well, I have many questions, but I'll ask one of them. And I also have a comment on this previous discussion, because in the models that I've studied in quantum field theory, it's really important to get a solution to know that the energy is unbounded from below, but doesn't seem that there's any way to put this into your picture. So this is very fascinating.
Yeah, I know. Like to do that, I personally never found the time to look at this question. I do think, because this is now spreading out a little bit more, this type of use of Hochschild and Dyson Schwinger equations and so on, there might be a fine day. At some stage, maybe somebody should look at the energy momentum tensor from this view. Something like that, what its Dyson Schwinger equation, so to speak, would be. But nothing has been done yet, which doesn't imply it's impossible.
Yeah. So could I ask a question?
Yeah.
I mean, I've lost track of what you're doing for almost 20 years, and it's fantastic, all the new structures that you seem to have found and the connections with different branches of mathematics. And I wonder two things. One, is there a place where there is a reference book for the theorems between the physics and the mathematics, so it's possible to understand precisely what the statements now are? And secondly, is there some connection with what your picture and the work of Nima Karni Hamid, which also has some connection with perturbation theory?
Yes. The first question, there is no good one review article at the moment which collects everything what is important and we have done in the last couple of years, but I signed a contract with Oxford University Press to write a book which does precisely that, but it takes another year or two until this book will be there. There are a couple of, if you look at, for example, a joint paper with Francis Brown, there is only one. This actually summarizes very nicely how renormalization looks from the parametric viewpoint combined with this Hochschild. It's a rather technical paper, but it's a very instructive paper. And a former student of mine, who is now a professor in combinatorics in the maths department in University of Waterloo, has written a nice little book on our approach to Dyson Schwinger equations, or at least that comes out. So for the second, what your second question was?
Connection to Nima.
Oh, yes, right. That's funny, because about half a year ago I gave a talk on this, maybe a little bit more addressed to physicists, where at least some students and postdocs of Nima were hanging around. And basically, the feeling they are ended up with is, or which we all ended up with, that the structures which I see from my boundary operator in outer space and the cell decompositions which I see there are very, very, very similar to the cell compositions they do related to cluster algebras and all these permutohedrons and whatever come up, and that the connection is in particularly strong for massless Feynman diagrams. Now, all my interests are at the moment geared toward massive Feynman diagrams, which has to do with Spencer Bloch's interest and our joint collaboration on Kreimer rules. But in principle, I do believe that the combinatoric structure, and I think it goes as far as saying that I do believe that the combinatoric structure which Karen Frogman discovered when she was studying outer space is a combinatoric structure which is in disguise very familiar to Niemann. And I think that connection goes by the fact that Niemann understands how he relates to tropical geometry, basically. And there is a lot of connection between tropical geometry and physics and what Niemann is doing. And tropical geometry, Karen Faulkner would say, is just a modern name for the structures she had in outer space, only she did it 10, 20 years before people started an interest in tropical geometry. So what we try to have when the pandemic is over is to have a workshop where people from outer space, people from tropical geometry, people from, say, the NEMA land of things, and people from our land of things get together. And this is probably happening in summer, late summer next year. So there is a gut feeling on both communities that we are looking at very similar structures.
So if you look at the progress up to now, can you say that the physics has made some important contribution to mathematics, or that mathematics has made some new insight into physics, or is it still in the gestation stage?
It's somewhat far into gestation, let's put it that way, with dramatic events maybe coming up. But I think right now, I can't say that one is feeding more into the other, but I do feel that they are coming much closer together recently. So there is a larger growing community of algebraic geometers who very, very dedicatedly look into the algebraic number theory or the transcendental number theory of Feynman amplitudes and try to understand what this has to do with the structure of cluster algebras, for example, in tropical geometry, and with all the outer space structures which we are having over there. And I think at this moment, a person who is very central to that is probably is Francis Brown, because he's a collaborator of mine, but also collaborates with people who are closer to NEMA. And there is a 2 or 3 year old little paper on the work of Francis and myself and people around us in Quanta magazine. But I do think that in 1 or 2 years from now, we can actually answer many of the questions which were left open down there. But I don't think that mathematicians informs physics more than physics informs mathematics at the moment. I think it's pretty much eye to eye.
It's fascinating.
Well, I like it.
Excellent. Other questions?
Concerning the algebraic geometry, there are many algebraic geometers who don't see any particular role for the complex numbers. And so some things from about the motive thing also suggests that there should be geometry around, algebraic geometry around, where all that would generalize to other fields. So do you have some comment on that?
To have a little bit of free space here, maybe here. Now, the algebraic geometry is precisely basically saying we look at one Feynman diagram, say this one, phi to the 4th theory, fascinating little diagram, and when you just look at its leading contribution, say, when all external momenta squares are equal and 1 q squared, then you get a 6th zeta of 3 times log, simple log q squared. And it's a 6th zeta of 3 which brings you the algebraic geometry in here, because you want to understand where this trilogarithm is coming from, and you have to look pretty much into the algebraic geometry and the motive which comes from assigning all my graph polynomials to this graph. So the algebraic geometry, for the time being, does it graph by graph. The ingenious thing which Karen Faulkner constructed, and she is not an algebraic geometer at all, she is maybe a geometric topologist, or she calls a geometric group theorist or whatever. When she invented the outer space, she did something which is very close to things Maxim Kontsevich were doing all along when he was looking at graph complexes and so on. She was just asking herself, if I get a graph, there's a natural cell I can assign to a graph. This has a spanning tree of length threes or in a certain cell of a certain dimension, and I can glue these graphs together and I go to higher dimensional cells. And then I can have two-dimensional cells which are co-boundaries of three-dimensional cells, and I keep gluing. And I construct a space which has many mysterious properties. Amongst them, it has a property that's a retractable space. That's an amazing theorem which he proved. And that tells you something at the end of the day, how all these Feynman integrants glue together. And I think this is the largest theory beyond algebraic geometry. We have to put algebraic geometry right in the middle of the study of graph complexes. So in the middle of the work by Thomas Wilwacher, Maxim Kontsevich, and such places. And Karen Vogtmann is coming from that work. She has written this very nice paper on a theorem by Kontsevich, which basically tells you how to look at A infinity or C infinity or L infinity algebras, starting from associative, commutative, or Lie algebras, and explaining this, how to go to this algebra, but just by studying graph complexes, by a procedure which initially she called mating spiders, which is basically having graphs with external edges, and they can mate and maybe form a bigger graph with lesser external edges. And actually this is behind this gluing procedure in outer space, and this is behind, you now put them on the Mars shell, then actually you find a little S-matrix theory, but you find also that a certain graph is made from gluing these things together by putting something on the Mars shell. And this whole of algebraic geometry, which comes from study of graph by graph, must sit somewhere in this whatever infinity algebras which have been constructed, and new of them, just because the operands are exploding by the day, you have little disk operands and you name it. But much of that has to be repeated and much more dedicated for Feynman diagrams. It's well understood for the representation theory of free group. Something is understood for Teichmüller algebras, but we need to dedicate it. We need to understand this as a function of the representation theory of the Poincaré group, because it's a representation theory of the Poincaré group which tells you which quantum field theory I'm looking at, because it tells you which edges and vertices I do allow. So if I have spin half, spin 1, spin 0 coming in there. So there's a big question mark in representation theory. How do you go to graph complexes with a dedicated representation theory of a Poincaré group, such that when you fix graph by graph, you recover the algebraic geometry, which should be there, but also you maintain all the nice, fancy graph complexes structure which started their life some 20 years ago with Kontsevich. That's basically where we like to put things for the time being, optimistically speaking.
More questions, comments? Well, let's thank Dirk again for a fascinating talk, and I will stop the recording and we can continue less formally.
Thank you.
Thank you.